Okay, let's do physics. Uh-oh, gotta plug my little input device in here. It's gonna come to life. There it is. All right, let's deal with error and uncertainty. So just give me a second here. I'll pull up what we were looking at before. So just a little reminder, we looked at the concepts of accuracy and precision, and we've been talking about the fact that there is some uncertainty inherent in any measurement that you make, right? So if you have a millimeter ruler, any measurement you make is plus or minus half the last readable digit. So on a millimeter ruler, it's half the last readable digit. The last readable digit is the millimeter, or the tenth of a centimeter. So it's plus or minus 0.05 centimeters. So a reading you might get could be like, I don't know, 27.72 plus or minus 0.05 centimeters, for example. Now, in reality, there's going to be a true length for the object, okay? And, you know, it might be, if we had omnipotent powers, that this is 27.72465513. I'm just making things up. Etc. centimeters, right? That could be the true value. With our ruler, though, we can only really access to here. And not only that, this has to be an estimated digit. We're saying it's a little bit more than, you know, 7, but a little bit less than 8. So somewhere in there, and we estimated that digit. These are inaccessible. I don't know how to spell the word inaccessible. Is that how you spell it? It's definitely not that. Let's try that again. How about I just go not accessible? I don't even know how to spell that word. Able? Accable? Man. Not ones we can measure. Sorry about the spelling issues. Okay, so how could I get access to these? What's one way I could get access to a few more of these? Yeah, right, exactly. I could get, say, calipers out. So the caliper basically gives us access to two more digits, right? So if I use a caliper, I can get a more precise measurement. So that's kind of what we're getting at here, is that your precision is going to be limited by the tool that you're using, right? So with a caliper, you get down to here. This is a digital caliper. And we talked about uncertainty on an analog measuring device. So if I use a normal ruler, it's half the last readable digit. This is a digital caliper, though. It's got a digital readout. What's the uncertainty on this thing? Anybody know? So we might not have covered that yet. Whoops. But on a digital readout, it's just plus or minus the last readable digit. The reason being is that because, you know, on a millimeter ruler, your eye can actually see where that, you know, that point's resting. If you know, if this is the 7 and the 8's over here, you can see it's a little more than 7. It's not quite 7.5. So we estimate that to be 7.2, right? In terms of millimeters, that is, right? In terms of millimeters. So that's where our estimate comes from. With a digital one, you don't have the ability to estimate. You're sort of relying on the circuitry to do that for you. So the uncertainty is not half the last readable digit, but it's plus or minus the last readable digit. Lots of times that's better anyway, though, because it's a more precise measuring tool. If you're looking for more precision. Sometimes more precision isn't really what you're after, but in the case where you want the highest precision possible, something like this is capable of measuring more precisely than just an everyday ruler, okay? So with the caliper, we might get a readout of 27.7246, because you get access to two more digits. You can see there it's to the nearest hundredth of a millimeter, so tenth of a centimeter. There's your millimeters, tenths of a millimeters, and hundredths of a millimeter, and your plus or minus 0.0001, right, equal plus or minus the last readable digit centimeters. Okay, so that's the kind of measurement you could get for this line from here. But still, it's got limited precision. All of this stuff is unavailable still. Can you get better calipers? Probably. But at a certain point, you're going to run out of technology's limits to precisely measure things, right? So if we look here, back up at the target, what we're going for is if the true measurement of some value, and like for something like length, which, you know, you put your caliper on and you measure, and it's probably going to give you basically the same reading every single time. You know, measuring the same thing over and over and over again doesn't really help you. But if it's, say, something like where you're required to do some timing, right? And you're using a stopwatch, right? And there's going to be some human error added into there, right? Because you're trying to like visualize it. What you usually get is you get some sort of scattering of your values around what the true value is. So if the true value, this, you know, whatever it is in terms of you know, the actual reality of the size of that object, with all of its precision, if that's the target you're trying to reach, okay, this is basically as good as you can hope, because you have some uncertainty in your tool, and you acknowledge that, and because sometimes there's you know, human aspects to measurement, or there's just like random errors kind of floating around in the world. It's expected that you aren't going to nail that directly, or it might not even be physically possible to nail that directly, but the best you can do is this. Now, if I took all of these measurements, say these 4 measurements, and I averaged them out, they should pinpoint me really close to the true accurate value, okay? So this is a highly precise and very accurate measurement. This is an accurate measurement, but it's much less precise, okay? So we're using a tool that's less precise. I mean, this might represent the measurements with a millimeter ruler, and this might represent the measurements with a caliper. If I average them out, though, they're both going to average out to pretty close to the correct value, okay? So we repeat measurements quite often in sciences to account for the fact that we might have these sort of like what are called random errors. One time we might measure a little high, one time we might measure a little low, but over time and over multiple measurements, we zero in on the correct one, okay? How would we get something like this, do you think? It's very precise, but it's clearly not accurate, okay? So we've got a nice small like kind of variation in our measurements. They're very like, you know, close to each other, but they're not on target. What causes something like that? Julian. Good. So this has a name. It's called a systematic error. Systematic error. Okay? And one place that can come from is an improper calibration. All right? So if, you know, if it's, say, a scale where I'm weighing things and I calibrated it with, you know, standards, and let's say when I was supposed to put a 500-gram standard weight on, I put a 1 kilogram standard on, okay? Well, now the thing thinks that every time I put 1 kilogram on there, that's actually only 500 grams. So it's a zero offset error, actually, is another way to put that, okay? Improper calibration and get a zero offset error. Sometimes those matter and sometimes they don't, okay? I'll tell you about how or why, okay? So a zero offset error means an improper calibration. All my measurements are going to be out by the same amount, all right? So I don't know, let's say the caliper at the factory was made wrong, and when they were like originally like setting it up, they took their you know, their 10 centimeter long standard that they were going to set in the machine's memory as 10 centimeters, and they put it in as 5 centimeters. Well, now it's going to be reading off by under 5 centimeters all the time. All right, so it's going to shift you off the true value the same for every measurement. Okay, does that make sense? It's called a systematic error. It's if you're looking for this value, but you're always getting that value, okay? But you're getting it very consistently and all the time. Okay, so that's a systematic error. The little variations that you expect and you can't really do anything about except try to account for, those guys, the little fact that you don't get the exact same value every single time you measure, those are called random errors. Okay? And we try to fix or account for those. Count. Does that look like the word account? Account? Not really. We account for by averaging multiple measurements. So you'll notice that the target, there's 4 shots there. We usually repeat measurements a minimum of 3 times when we're doing science. Okay, it's kind of the rule of thumb. In some cases, it doesn't make sense to remeasure. Like if we're just measuring the length of a line, and we're using the same tool, that's kind of a case probably where you're going to get basically the exact same measurement every single time. But this is more for if you're like trying to, I don't know, say measure the time it takes for an object to fall. Well, there you're using a stopwatch and you're going to get variation in your measurements because you have to like physically interact, all right? Now people always want to say there's human error there's human error. In science, we don't really, or we try not to use this term human error. What it is it's just random error in the measuring process, okay? Can we reduce the size of random errors? What's one way we could say, like, by dropping an object? Say we're trying to measure the time it takes for an object to fall 2 meters. How can we reduce the random errors that we're getting in a case like that? What could we do? Instead of just using a stopwatch with my thumb, I could do what maybe? Use Julian? Yeah, but I'm thinking more just like how I'm actually pulling the measurements out of what I'm observing, right? So I was thinking more along the lines of like, what if I video it and I use the, like the time on the frames of the video? Or what if I set up like an electronic timer that like starts when I press a button and that also like releases the, the ball, and then it, stops it when the ball hits some sort of like, sensor at the bottom. Okay, so I can remove the human aspect a little bit from it. I still might get slight variations, but they're likely to be more tightly packed, right? Yeah. Yeah, I'd use tools that bring along less uncertainty. Yeah, exactly. Lower uncertainty, that not necessarily more precise, but less uncertain. Yeah, more precise. Yes, agreed. Correct. Okay. And then what about this? Well, this is just kind of like bad measuring, isn't it? We've got a bad tool, or we've got an imprecise tool, and we've got a systematic error at the same time. So really, if this is where we're doing our science, we're not going to get any like really usable results. They're going to be totally out to lunch. Okay, so we don't want that. We want to strive for this. Okay, that means to using the most accurate and precise tools we can get, trying to avoid systematic or zero errors, but accepting that there's going to be some small, random errors that come along with our measurements, and then thinking of ways that we can do a better job, a more precise job. Okay, so there we go. So how do we judge the quality of our work? Let's try this out. So we'll do a little sample problem here. It's going to take a little while, and then we'll try to judge whether or not we did a good job of it. Okay, so you guys are actually going to do this in a real lab, so pay attention here. So density of a cube. Alrighty. Is that a straight line? I think so. Let's say you have a cube made of metal, and it looks like this. And you want to know what is this cube made of? That does not look like it's going to be a cube. Fix it. Better? I used to be faster at drawing cubes. Get rusty with the software here. There we go. Where's your cube? Okay, so how do you want to measure this cube? So if we want to find its density, sorry, I guess I should explain more. Calculate its density and compare to a chart of known densities. Okay, so that's what we need to do. We need to find its density and compare to a chart of known densities. So do you guys know what density is? What is density? Yeah. Okay, so how compact it is, sure. Can you give me like a more mathematical definition of it? Nate? Good. Mass per unit volume. So since we're dealing in, the metric system here, let's go with grams per cubic centimeter. Or properly written, your units will be in grams per cubic centimeter. Like that. Okay, so mass per unit volume. So data that we need. How much does this thing weigh on a scale? Okay, how much mass does it have? And we can measure the length, the width, and the height. Okay, now remember, every one of these measurements brings a little bit of uncertainty to the table. So as we're doing our math, we're going to need to be propagating through the uncertainty. Okay, so let's let's get on with it here. Let's say this is a I don't know, let's say this is 11.24 plus or minus 0.05 centimeters. Going this way. Let's say this one is 11.27 plus or minus 0.05. And that's in centimeters. And let's say it's like 11.09 plus or minus 0.05 going this way in terms of centimeters. So your first task is going to be to calculate the volume with uncertainty. Okay, pause for a second. All right, so 11.27, we'll start with that one. We've got 11.24 and 11.09. So first step is to multiply all those things together. And what will we get? So I get 1404.823532 centimeters cubed. Okay, clearly there's too many significant digits here. There's no way I can know to the nearest, I don't know, what's that, 10th, 100th, 1000th, 10,000th, 100,000th, millionth of a cubic centimeter, because the closest I could get was to the nearest 100th of a cubic centimeter in my initial measurements, and even those values were estimated. So clearly too many sig figs. But we'll just leave it like that for now. Okay, we won't round it just yet. And now we also need all of our percent uncertainties, because since we're multiplying, we have to add up the percentage of uncertainty that each of these brings to the table. Okay, you can't just tack on some, some of these things. This is not how it works for multiplying. So each one has the same amount of uncertainty. Okay. Okay, so there's our percent uncertainties. Now we have a set value for uncertainty in each measurement. But as percentages, you see where you have a lower measure, the percent uncertainty is higher, right? And if you had a really low measurement, you could have a very, very high percentage uncertainty. Just keep that in mind. Sometimes when you're designing experiments, there's opportunities to measure larger distances versus smaller ones to get the same results, or times, right? If you measure times for, say, like multiple repetitions of something, like say a pendulum swinging, you're going to get a lower percent uncertainty than if you do it for just one swing, because you're extending out the size of your measurement. Sorry, just on that one, this is actually, I just rounded wrong. This is actually 0.45. But still, the point still stands, right? It's a slightly larger fraction of the overall because it's a lower measurement, okay? All right, so then what we do is we just take these values, so 0.44, 44, and 0.45, and we add them up and we get plus or minus 1.33%. Okay. So basically, if you were just asked for volume, you would report it as 14. You have 1, 2, 3, 4 sig figs, 14O round to 5, plus or minus 1.33%. We generally don't leave it as a percentage uncertainty. We would convert it back to an absolute uncertainty. So to do that, you take your value here, and you get that. Gives you that. So your final way of writing this out would be 1405 plus or minus, and it makes sense to just round so that your lowest sig fig is the same on each one. So that rounds to 19. So just that little bit of uncertainty in your original measurement means that your cubed volumes have, I don't know if you call that significant, but probably much larger than you would suspect uncertainty. So those little input values essentially magnify into giving you a result that's maybe not as precise as you would hope. All right. So definitely something to keep in mind. Now we're not quite done yet because we were asked to do density. So a rule of thumb is don't round values until the end. All right. So the next thing we'd have to do is weigh this object. So let's say we put it on a scale. Let's grab it here so we can see it being weighed. Let's group it. Copy it. Bring it on down. Okay, so we fire this thing on a scale. Let's see here. What does a scale look like? Very rudimentary scale. And the scale is a digital scale, and the readout on the scale is that this is, let's see here. I don't know. How big did I say it was? Like 10 by 10 by 10? I don't know. Let's say it's like, okay, so this scale gives you a reading to the nearest tenth of a gram. So we would write that it is 472.6 plus or minus how much? The digital readout. 0.1 grams. Perfect. And seeing as how we're going to do a division with the number that we got for volume, so we're going to put the mass and it's going to be divided by the volume. We're going to do a division, so we're going to need a percent uncertainty again in order to propagate the error correctly. So 0.1 over 472.6. Let's make sure I did the math right. Yeah, really small. So we get 0.02%. So very, very small amount. Okay, now we'll do the density calculation. Mass, volume. All right, so our mass was 472.6 grams. And we have 1404.82. 3532. Okay. Oops. So you get something like 3.36412 times 10 to the negative 1 grams per cubic centimeter. Right. Now we have to add the percentages of uncertainty onto each other and tack it onto my value that I have. No?
Oh, sorry, I'm reading it.
Yeah, it's like 0.336 without using scientific notation. So we get 1.35%. Okay. All right, so now let's round it. We're allowed to have 4 sig figs max. There's 4 here, and there was 4 in our initial cubic centimeter one, so 4 sig figs. We could write this as 3.364 plus or, oops, 4 times 10 to the negative 1 plus or minus 1.35% grams per cubic centimeter. Okay, so far so good. And then you can change that to the absolute value. Okay, so in terms of absolute value, it should look like that. Okay, and that should line up with the last two values that we have there. That's grams per cubic centimeter. Okay, done. Density with our uncertainty attached. Okay, now the next thing that we're going to bring into focus here is called an error analysis. So how do we know if we've done a good job? Some people call this just like a percent error. All right, let's say you go to the literature, you go to a big book, and you look up the density of whatever metal it happens to be. Okay, so let's call it unobtainium. So you go to the big book of science, maybe like the CRC handbook or a website that has this kind of information on it, and you figure out that the literature value is 3.51 times 10 to the negative 1 grams per centimeter cubed. Is that the value you got? It's not. Is it a good value? Like, is your value good? Yes. Who says it's good? You did a good job in this lab. You found the density. Some people say yeah. Who says no, you didn't, because you didn't get the right value? No one says that? Well, maybe there's a way that you can decide if it's good or not. Okay? Okay, so just before we get into the like official way to do this, the quick thing that we can do is we can say, okay, the value that I had here, 3.364 times 10 to the negative 1, I could see that the true value is higher, so my value is a little bit low. But seeing as how I have an uncertainty range on here, what's the highest value mine could be? And is it above this or not? Okay, if it's above it, boom, we're within a fair range, right? The range that we're suggesting is where the true value falls. So what we could do is we could say, okay, so what we're going to do is we're going to say, we're going to take this value and we're going to multiply it by, let me just think here, 1.0135, and we'll see what we get. So what we're doing is we're taking this value and we're adding on to it the 1.35%. Okay. So what does this tell you? The measurement that you took, including its uncertainty, cannot get you to the point where your true value falls within the range that you're allowed, okay? That you've allowed with your uncertainty. What does that tell you about your experiment? There's an error in it, isn't there? So if we scale back up to here, way up, we grab this thing, let's copy it, okay, and scale back down. We can look at this and we can say the target, right? What we were aiming for in our measurement was this right here, okay? Do it in a color that you can actually see. Now, what actually happened? Where did we end up? If I were to draw dots on here, how would ours be represented on these targets, like our experiment? Like, we didn't quite nail the target with averaging. So what would it look like here, do you think? Where should I put my dots to represent what we did? Now, we only did one measurement, too. That's the other problem. Okay, because we could maybe remeasure, twist that, turn that cube around, measure it from, you know, different sides, measure all the sides and average them. There's other ways we could have done it. We chose to just take one measurement. So what happened was we ended up slightly below the value we should have, okay? But we weren't off by much, really, okay? So what does that tell you about the arrow that we shot? It has what in it? It has something, has some kind of problem. Does it have random error? Sure did. We accounted for the random error. Yeah. So that's in the plus or minus 0.05 that we propagated through as we did our experiment. So what must happen is once we've accounted for random error, if we're still out, there's a systematic error. And this is where people are going to say, when they're writing up their lab reports and they're trying to explain why they didn't quite get the value that they had hoped, they'll want to say it's because of human error. You can't say that in IB, in science. Human error is not allowed. Basically what you're saying is like, I don't know how to use tools. I don't know how to read what my tools say. Human error, not allowed. You guys are scientists. You know how to use a ruler. right? You know how to use a scale. Human error is not allowed. There's something else going on. So what might it have been? Okay, yeah, right. Okay, one thing could be um, tool was inaccurate. I used a 10-cent cheap plastic ruler to measure the size that Mr. Johnson gets in bulk from who knows where, you know, and they're probably not like up to standards, let's say. What else could it have been? There'd been a zero error on the scale. Okay. Could have been our technique. Now you might say, but that's just human error. Okay, maybe. But there's a lot more to it than just I don't know how to read a ruler correctly, right? Like maybe there's some dents in the metal. And if that metal were like lead in real life, lead's soft. So the lead cubes that we might use to measure this could have dents in them or bent over edges or whatever, right? Dents in the metal, let's say. Um, what else could it have been? Is it possible that you uh, are like at a really hot or a really cold temperature? Okay, so there could be a temperature error, right? Because you'd have to look in your book and it'll tell you the density at a certain temperature, right? Especially if it's a very precise measurement, more precise than that. Densities change with temperature, right? Because objects expand and contract. They become less dense the warmer they are. So there's all sorts of stuff that having a systematic error forces you to think about. In science up till now, you're probably just like, I didn't get the right answer, human error, I'm done, right? But now you got to think a little bit more. So even along those lines, if you got a value that's lower than expected, would that mean that the temperature, if say temperature is your go-to on this, would that mean that the temperature in the room was too high or too low? Do you think if your value ended up as a lower density than expected? Was the temperature in the room too high or too low? Kaylee. Too high because things become less dense and you got a lower density than expected. And then you have to check, was it actually too hot in the room? And if it wasn't, if that's a variable that you controlled for, then you know that can't be the right thing. But if it was like the air conditioner was broken and it was like 110 degrees in the room, I should speak in Celsius, it was 30 whatever, 8 degrees in the room or 39 degrees in the room, boom, I've zeroed in on what the issue is. And I would say, when I do this experiment again, I'm going to control that variable and I make sure I do it in a room that's 20 degrees, let's say. Okay? So this is the kind of thinking you have to do when you're doing these experiments. Now, how do I officially deal with this? I'm not just going to go every time and just be like, well, does it fit in there? So the way we do this is a true error analysis. And there's just like a little formula for it, which you've seen already, but just to remind you, it is actual value from the book minus the experimental value, and you take the absolute value. The reason being is because you might be above or below. But we don't really care, at least at this point, if you're above or below. Okay? Actual minus experimental divided by actual times 100%. So if I go up to here, my actual value, 3.51 was 10 to the negative 1 minus 3.364 10 to the negative 1 absolute divided by the actual. Okay, all the units here are grams per cubic centimeter. And actually, I don't even think, sorry, you don't even need to deal, because you're just doing an error analysis, don't worry about units, doesn't matter. And they'll cancel out anyway, so it does not matter, because percent error is unitless, right? All right, so let's figure it out. 3.51 Okay, so I get about 4.1%. We would call this the error or percent error. All right, and this is gonna give you like a numerical measure, basically, of how well you did. So you're off by 4.1%, but you're only allowed to be off by 1.35%. Okay, so we call that the allowable uncertainty, or allowable error is another way of putting it. Allowable uncertainty from random error is 1.35%. So 1.35% of the 4.1 can be explained away by saying that's just random error because of the measuring tools that I used. Okay, but what can't be explained is the difference between the two. So about 2.8% of that variance or difference has to come from somewhere else. It's not a lot, not a lot. And it might be as simple as you had a cube that wasn't a perfect cube, let's say, or maybe it is because the temperature is too high or too low. It's your job as a scientist to try to track down where that comes from. Now, what would have happened if you did this and you only came out with a 1% error? What would you say then? Let's say you did this calculation, a minus e over a, and you only got 1%. What would you say about that? Yeah, Kaylee. Yeah, I'm in the allowable uncertainty. I did a good job. I read my tools correctly. I accounted for error, and I'm good. Not really any more needs to be said, right? I got what I expected to get. The value that is true fell within the range that I allowed for. Life's good. High five to myself. I scienced. Okay? How often does that happen in reality? Haha, rarely. Even with something as simple as a density calculation, especially when you're dealing with like really light objects, okay, um, you can have issues. All right, so when we do the lab, this is kind of the setup for it. All right, I'm going to end now. Any questions?